Okay, let's go ahead and start the standing wave problem. In this problem, we're given two fixed strings. We're told that the strings are identical. So if they're identical, we're going to assume that means that they have the same length and the same linear density. These are two important aspects of a fixed string. The strings themselves are identical. If string A starts oscillating at its fundamental frequency, string B begins oscillating in its third mode. And then we're asked to determine the ratio of the string tensions. So let's back up for just a second. And first of all, think about what equations are useful here. So we are interested in what's useful. Wave speed on a string. Wave speed is equal to square root tension divided by the linear density. And then, of course, the all-important relationship between wave speed, wavelength, and frequency that comes in super handy. All right, so we've got these two strings. I'm going to just kind of draw them out because I want a little bit of a visual here and have you, in our brains, we need to be thinking about the fact that these strings are identical and what are they doing. So I'll call this one string A, string B. So string A is in its fundamental mode. I'm going to draw it that way. And string B is in its third mode here. So I'll kind of sketch that out. And that helps me know right away what the strings are doing. So there's a really important kind of subtlety here, and that is that the problem says if string A starts oscillating at its fundamental frequency, string B begins oscillating in its third mode. So that happens basically because string A is driving string B. So the frequencies of these two strings must be the same. String B wouldn't just suddenly start oscillating at a completely different frequency. So these two frequencies are the same. So that means that the frequency, the fundamental frequency of string A equals the third mode of string B. And the third mode of string B is going to be 3 times the fundamental of B. Okay, so just kind of catch up with that real quick. So how I'm using this F is to stand for the fundamentals. So this here is the fundamental for A, and then this F sub B is the fundamental frequency of B. All right. So the all important step here is to set these two equal to one another by what's implied in the problem statement. So for fundamental frequencies, what I know is that, I'll let you think about that for a second. For fundamental frequencies, what do we know? Lambda is equal to, now let's say this has some string length L. We're not given that L, but we can call it L right now, and we know that the two strings have the same length. So for some fundamental frequencies, the wavelength is equal to 2L. That's always going to be true, right? Because the fundamental is this mode that has one loop that string A is depicting there in its fundamental frequency. So that's half a wavelength every time. So what I can do here is I can say, all right, what I know here is that the frequencies are the same, right? And I'm going to go over to the right-hand side of the page now. If this equation is true, I'm going to just solve this equation here for frequency. So frequency is equal to then wave speed over wavelength. So I'm going to go ahead and apply that for each one. If I know that the frequencies, I have this interesting relationship between the frequencies, the fundamental frequencies there, then I can say, all right, the wave speed of A divided by the wavelength of A is equal to 3 times the wave speed of B divided by the fundamental wavelength for B. And then I can kind of move on using this relationship, reminding myself that I can define the wavelength for the fundamental mode. So you might be wondering, like, why do I keep going back to the fundamental mode here? Why don't I? Well, the reason is that the fundamental mode, every time in one of these standing wave problems, I'm going to try to model for you utilizing what you know about the fundamental frequency. It's super useful, that fundamental mode. If you know the fundamental mode of a system, a standing wave system, then you can know all the other modes to it too. So once you know the fundamental mode, that's like the key that kind of unlocks the rest of the pattern. So that's why, even though there are different ways to solve some of these problems, I try to model consistently how to leverage the fundamental, what we know about the fundamental in order to solve them. Okay, so if I know that wavelength is equal to 2L and I know that the strings are identical, right, in these two cases, then I can work with this equation, rewrite this equation a little bit more here. So I can write this as 1 over 2L, and that's in place of the wavelength. And then substituting for the wave speed, I can sub in root, T, tension in string A over the linear density. Linear density is the same for both. I'm not going to subscript that. 3 over 2L times root tension sub B over mu. And then I'm just going to pause for a moment, and you might ask, well, how do we know the tensions are different? The tensions have to be different because these two strings, the strings themselves are identical, right? So the only thing that could make them have different modes or different, you could say the only thing that could make them have different fundamental frequencies, if you want, is that they have different tensions. And remember that it's the medium that determines the wave speed, right? And in this case, the medium is the string. The strings have the same linear density, so that's not going to cause any different wave speed, but they can have different tensions. If their tensions were the same, then they would both be oscillating in the fundamental mode here. But they're not, right? They're oscillating at the same frequency in different modes, so we know that their tensions have to be different. Anyhow, if I continue on with this, I can work this forward to solving T sub A equals 9 T sub B, and that gives me the ratio that's being requested here. T sub B over T sub A equals 1 over 9.